Hi there! Welcome to the 6th episode of the Digital Electronics Fundamentals series. Now that we have learned how logical ports work, it is time to put them at work in more complex circuits. Today we will start learning about flip-flops, which are the basic elements used in sequential logic like computers and communication systems. Let's begin! Flip-flops are usually made out of simple NAND or NOR ports. In this discussion we will concentrate on the NAND ports, with the understanding that whatever we say about flip-flops with NAND ports, it is valid as well for NOR ports. The first flip-flop we will learn about is the SR flip-flop, named after its two inputs, set and reset. It is a bistable circuit, which means that once we apply a certain combination on its inputs, it will retain the same output as long as the inputs are in the so-called latch position. Because of that, they are also called SR latch flip-flops. The main purpose of a flip-flop, whatever it is to store a state and preserve it until certain conditions are met to change such state. To do that, the flip-flop uses a double feedback between its two outputs and its inputs. Here is the basic schematic of an SR flip-flop. Q and not Q are the two outputs of the device, S and R are the two inputs, which with NAND ports are actually inverted. The wire between the output Q and the second input of the port at the bottom is the first feedback, and the wire between the inverted output and the second input of the port at the top is the second feedback. Let's figure out how this device works, and to do that, let's use a truth table. The inputs will be of course S and R, and we will have two outputs, Q and its inverse. The possible inputs will be 00, 10, 01 and 11. Let's assume that the two outputs are initially set to 0 and 1, and let's see what happens when we apply the inputs on the first row. Since we actually use the inverse of S and R, this means that we apply 1 and 1 to the two inputs. And this means that we are applying 1 to both inputs of the gate at the top, and therefore we will have a 0 at its output consistent with the current value. At the same time, we have a 0 and a 1 at the inputs of the gate at the bottom, which generates a 1 at its output, again consistent with the current value. Let's write down these results on the truth table. Now let's assume that the two outputs are initially set to 1 and 0. We have now a 1 and a 0 at the inputs of the top gate, which generates an output of 1 consistent with the new current output. And we also have a 1 and a 1 at the two inputs of the bottom gate, which generates a 0 at its output, consistent again with the current output. And so basically, with the first row inputs, whatever it is the current output, it stays that way with no changes, which we can represent on the truth table this way. We say that the flip-flop is in a latch condition, where whatever is the initial output, it stays that way as long as the two inputs S and R are both set to 0. Let's now see what happens when we apply the inputs from the second row of the table to the flip-flop. In this case, S equals 1 and R equals 0, and therefore we have a 0 and a 1 at the inputs in the schematic. Let's now assume that we initially have the top output set to 0 and the bottom output set to 1. Because of the 0 at the top gate input, the output will change to 1. And because now we have the two 1s at the input of the bottom gate, its output will change to 0. If we had started with a 1 on the top gate and a 0 on the bottom gate outputs, they wouldn't have changed. Therefore, with this input configuration, the output is forced to be like this, a 1 at the primary output, Q, and a 0 at the inverted output. If we do a similar reasoning on the inputs at the third row of the table, because of the symmetry of the diagram, we will have a 0 at the top output and a 1 at the bottom output. Let's write this finding on the truth table. And now let's work on the last row, where both S and R are set to 1, and therefore both inputs on the diagram are set to 0. Because both inputs are set to 0, both outputs of the gates must be set to 1. However, when we move back the inputs to the latch value, since we won't have anymore a stable condition, one of the two outputs will move to 0. Only one, because we have to move back to the values of the first row of the table. We therefore say that having both ones as the inputs of the flip-flop is an unstable condition, and once that condition is resolved, we will have a random output, either a 1-0 or a 0-1. We can indicate these results on the truth table by not specifying any value and using instead a dash symbol. Let's now design a circuit to verify these results experimentally in lab. Here is the schematic of this circuit. At the gate outputs we put an LED in series with a resistor to limit the current. Anytime an output of the gate has a 1 and therefore has a voltage of plus 5 volts, the corresponding LED will turn on. On the input sides, we will apply the 1s to keep the flip-flop on the latch state with a couple of resistors connected to the plus 5 volts. And a push button will be able to ground the gate input and therefore set it to 0 temporarily. This is the circuit mounted on a breadboard. This IC is a SN7400, which contains 4 2-input NAND gates, and this is its internal representation. I assembled the circuit using these 2 ports on the left, leaving alone the 2 ports on the right. In order to avoid interferences from the gates on the right, I avoided an unstable state by connecting both of their inputs together and to the ground. This way, the 2 ports will have a stable one as their outputs. The 2 ports on the left are instead used for the actual circuit right here. These 2 green wires are the 2 cross connections visible in the schematic between an output and one input from the other port. Here are the LEDs connected to the 2 outputs, and I have chosen the orange color for the top gate and the green color for the bottom gate in the circuit. These 2 are instead the push buttons to apply a 0 at the S and R inputs of the flip-flop. Let's power up the circuit and see how it works. I will be using a power supply of plus 5 volts since this is a TTL IC. And right now we have the not Q output set to 1, while the Q output is set to 0. If I now push the reset button, no matter how many times I do it, the output will not change, as expected from the theory. If I push the set button, the flip-flop will switch, and now the Q output will end up with a 1. At this point, whenever I push the set button over and over again, the flip-flop will remain stable and the state will not change anymore. To make the device switch again, I will have to push the reset button. And we can change the flip-flop state back and forth by pushing alternatively the 2 buttons, the S button and the R button. Now, if I push both buttons at the same time, we will get a 1 at both outputs. But then, when I release them, the outputs will go randomly to one of the 2 stable states. And that's why a 0-0 input configuration is not considered stable. Let's now look at another version of the same flip-flop that allows for a state change only when a certain condition is satisfied. We can think of a third input that allows the other 2 to work only if that input is set to 1. We call such third input a clock input, and it is called a clock because in complex circuits a periodic clock signal is used to force all the logic ports to set to a new state at the same time, with a cadence that is imposed by the clock signal itself. We will talk more about this topic another time, but for now let's just think of the clock like a gate signal that allows the flip-flop to work only if its value is 1. Here is the schematic of such a clocked SR flip-flop. You can see on the right side the SR flip-flop we have already studied. On the left side there are 2 extra NAND ports. One input from each of the ports constitutes the S and the R inputs of the flip-flop. The other input of both ports is connected to the other one and together makes up the new clock input. In practice, when the clock signal is set to 0, both NAND gates on the left will have an output of 1, and these outputs are applied to the SR flip-flop, which will then be in its stable latch state, thus holding stable whatever it is in the current output. However, when the clock is set to 1, then the output of the two NANDs on the left will depend on the inputs S and R, and in particular will be the inverse of S and R, which are exactly the names we gave to the inputs of the SR flip-flop. Can you see now why we use that old naming with the regular SR flip-flop? With this configuration, now the inputs to the whole circuit are exactly S and R and not the inverse. Let's now use a truth table to represent that. This time we are going to use 3 columns for the inputs, the clock itself, the S and the R. And we are also going to visualize both Q and not Q. We have 4 possibilities for S and R, 0, 0, 0, 1, 1, 0 and 1, 1, and they will repeat for the values 0 and 1 of the clock. Let's take a look at the 4 rows where the clock is 0. If the clock is 0, whatever is the value of S and R, the output of the 2 logical ports on the left will always be 1. And this means that the SR flip-flop on the right will be in the latch state, where whenever the outputs are, they will never change. On the last 4 rows, instead, since we have always a 1 as the clock value, whatever we put on S and R, it will be inverted on the output of the 2 ports on the left. The inputs of the SR flip-flop on the right are therefore not S and not R, and so the output of the flip-flop will reflect those of the regular SR flip-flop. And now it is time to verify this behavior in lab. Here is the schematic of the circuit we will be using to verify the behavior of the clocked SR flip-flop. As in the previous circuit, I have put a couple of LEDs to visualize the output of the flip-flop. The inputs, instead, are connected with the resistors to ground, since this time we are dealing with the actual signals and not their inverted values. 3 push buttons connected to the plus 5 volts will bring the inputs to the logical value of 1 when activated. Here is the circuit built on the breadboard for this test. In the center we have the same SN7400 with 4 2-input NAND ports. On the left side we have this time 3 push buttons, the one on top for the set, the one on the bottom for the reset, and the one in the center for the clock signal. On the right side we have again 2 LEDs, the orange one for the Q output and the green one for the inverted Q output. Let's power up. And right now we have the Q output set to 1, and whenever I push the set or reset buttons, this state does not change as expected. But now, if I push the clock button and the reset button at the same time, the flip-flop changes state and the inverted output goes to 1. Once the clock is 0 again, whatever I do now does not change the state any further. And if I push the clock button again and the set button now, the flip-flop switches again. Pushing again the set button does not cause any further state change, but if I push the reset button, then the state changes again. Let's now see what happens if we push all 3 buttons at the same time. While all the buttons are pushed, and therefore all the inputs are set to 1, both LEDs turn on. But, as we know, this is an unstable configuration, and so as soon as I release all of them at the same time, only one LED stays on, randomly. This time it was the Q LED. This time was the other one, and so forth. The SR flip-flop is basically at the core of any other kind of flip-flop, and it is important to have a good understanding of it. The clocked SR is the first variant of the SR flip-flop that we have seen. In future episodes we will examine other variants, and we will keep making modifications to solve different kinds of problems. All of that will be completed with practical examples. Soon we will be able to see how counters work, both binary counters and decimal counters, as well as many other devices, all having at their core the SR flip-flop. To avoid missing any of these future episodes, don't forget to subscribe to the channel and to click on the notification bell. See you in the next episode, and as usual, happy experiments!